It's hard to manipulate the factorials. It's very easy to manipulate the x's and the exponents, things like that. So in number 10, it says use a known series to determine the function represented by that. The first thing I'm going to look at is the factorials. And the factorials seem to be a 1, then another 1, then 2 factorial, and 3 factorial. Here is where, like I think about your quiz tomorrow, a test coming up later this week, here's where I say to myself, if they know the 4 important series, they got a good shot. If they don't know the 4 important series, they got no shot. Do you see my reasoning there? If you don't know those 4 known series, I don't see how you could possibly answer this question in any kind of a realistic time frame. But if you know your known series, this is doable. So with that factorial pattern, like I said, it seems to be like 1, 1, and obviously 2 factorial, 3 factorial. Which known series does that seem to go with? E to the x. Yeah, so we'd start there and say, all right, well, e to the x, our first hint with factorials, we'd say e to the x then is equal to 1 plus x squared over 2 factorial plus x to the third over 3 factorial, dot, dot, dot. And then we start to look at the other parts. Now that we've said, okay, we got the factorials to kind of line up, you look at the other parts, and you can see, of course, that the 1s line up exactly, but then everything else pretty much doesn't. Do you notice that it's an alternating series now? Okay, and then of course the exponents are all even, 2, 4, 6, dot, dot, dot. So we want to ask ourselves then, what makes the most sense? Does it look like somebody has multiplied e to the x by something, or do you think someone has substituted, or do you think it's a combination of the two?
Can't you also take the derivative?
Can't you also take the derivative?
Yes.
You could.
I'm not saying that's definitely what we're seeing here, but isn't that an option?
Oh, yeah.
We put x squared in.
Oh, you're saying it's like, how could somebody have manipulated a series?
Yeah.
They could have integrated it or differentiated it. Yeah. Yeah, absolutely. Allie, I'm sorry, you said something in the middle there?
So I think they substituted an x squared in every time there's an x.
Okay, so if we try to construct this now, we'd say e to the x squared would equal 1 plus x squared plus x to the 4th over 2 factorial plus x to the 6th over 6 factorial, right?
Do you focus first, or do you do the subtraction first? Which one do you do?
What? Well, hang on. Let's hold on. That means stop talking. Do you see how Allie has gotten the exponents to agree? But we still got this may be what Hayden was trying to get at. We still got like the minus plus thing. And it's still only pluses on what Allie proposed. So how could we get that alternating thing to show up? What do you think, Drew? Right, but what this is asking us to do, though, is use a known series to determine the function represented. So I can't just throw a negative 1 to the n on the front of the function. I've got to figure out what did they do to that series that then I would have to do to the function as well. Going exactly backwards. Was that Tess or McKinsey? No?
I was just going to say the negative in front of the x, right?
Which x? There's a bunch of them.
Wait, hold on.
All right. Any other suggestions? Because we're right on the doorstep.
You do negative 1 to the x.
Negative 1 to the x.
Times it.
Well, if I...
Negative 1 in parentheses.
To the what?
To the x.
To the x.
Plus 1.
No. I'm not sure how to address that. Yeah, you guys are wanting to multiply by stuff. And if you multiply by negative anything, isn't that going to make all of them negative?
Not if you do it to negative 1 in parentheses.
You're wanting there to be a series. You're wanting there to be a sigma on the front of it, right?
Why can't you do that?
That would be the nth term. I agree. So we could write an nth term for this. So plus dot 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 plus it would be sigma, and it would be x to the 2n over... Oh gosh, I wrote this wrong. This should be 3 factorial. Is that what you're going to say, Sydney?
Yeah.
I could see that look on your face, and I didn't make the connection until I wrote my nth term. There we go. So there's your nth term. So you're wanting to say negative 1 to the x or negative 1 to the x plus 1. Well, the the element within the sigma is n, not x.
I know, but if you if you times the whole equation,
By?
negative 1 to the 2x plus 1, why can't you do that?
No.
It works.
So you're proposing to multiply by negative 1 to the 2x plus 1.
Yeah.
I fail to see what that does. How is that going to cause it to alternate?
Well, if x equals 0,
No, there is no. So if x equals 0, then the whole thing would just be 1.
wait, so I'm confused.
No, the whole thing would just be no. Here's where you're getting confused. You're equating n with x.
Why can't I do
Because x is in both equations.
exactly?
Yeah, so n is different than x.
Okay. How about I show you?
I'm confused.
I agree.
I don't know how to do it.
How about I show you? So Reagan's idea of substituting x squared for x was a good idea. It was a very good idea. But there's one little tweak that I would make to it. Here it is. This would be it right here. If we substituted negative x squared, let's think about what would happen. We would get 1 still. That hadn't changed. And then in place of x, I would put negative x squared. Right? And on the next term, I'm going off of this right here. And then in place of this x, I would put negative x squared. So it would be plus negative x squared squared over 2 factorial. And then it would be plus negative x squared cubed over 3 factorial plus dot dot dot. So the idea here would be that whenever you take a negative to an even power, you get a positive. And whenever you take a negative to an odd power, you get a negative. So this would end up being e to the negative x squared equals 1 minus x squared, and it would just be plus x to the 4th over 2 factorial. And since you're taking a negative to an odd power, it'd be minus x to the 6th over 3 factorial. And you're done. Strange thing about this sort of thing is there is not a heck of a lot of calculus in here. The big part of the calculus is knowing kind of where the Maclaurin series came from, but the rest of it is substitution, multiplication. In the case that Hayden mentioned, there might be a derivative or an integral involved in some of these at times. That's obviously calculus, but this one right here was all about algebra. Not easy, but algebra. Question?
Whenever we look at these equations, do we have to do it like reverse? Should we always look at the denominator first before the numerator?
You should always look at the factorials first, I think.
Okay.
So if you look at the factorials, then that should give you some kind of a clue about where to start and where to start trying to look for manipulation.
Okay.
And then say, okay, what happened with the x's?
Would we have been able to do it with cosine because the numerators look like cosine? Or
No, there's only one function. With these, like I said at the start, I'll say it again, for any particular function centered at, in this case, 0, there is exactly one power series for it. There's no, I decided to make it a cosine or I decided to make it a sine. If there's just one option. Let's go back to the original question. It says, use a known series to determine the function represented by. So it's wanting to know the function that generated this. That's the answer, e to the negative x squared. That's the function that generated that series. We did that by going backwards. Can I give you a chance to practice this by yourselves? Why don't you guys try number 11? Again, using the principle that Grace just brought up, the idea is look at the factorials first. They should give you a clue about what's going on. And then once you've determined, okay, the factorials are telling me this, then think about what happened with the other stuff. So give it a shot. Try number 11. So here we go. Did you guys look at those factorials and determine the basic pattern? Sine, right? You got all the odd stuff going on. So maybe you'd think of this. You'd say sine of x is supposed to equal x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Please note, there are no n's in sight because there's no nth term. Nowhere did it say find an nth term, use an nth term, do anything with an nth term. There are no n's anywhere. This is purely dealing with the numbers and the x's. No n's or nth terms or sigmas anywhere. So I'm gonna ask the same question that Sydney did just a second ago. She's like, I get the whole factorial thing matches up. She said, how do I make the degrees one less? You divide, right? Isn't it like when you think about that question, how do you make the degrees in a polynomial one less than they used to be? Well, you divide. Because when you divide by like bases, you subtract your exponents, making the degrees something less than they used to be. So they need to be one less, and so we would divide by specifically x. So if I divide the first term by x, x over x is 1. The second term, x cubed over x, is x squared. So it would be minus x squared over 3 factorial. You divide the next one by x, so that would be plus x to the 4th over 5 factorial. We're starting to see that this pattern finally is going to match up really, really well. So the answer to the question, determine the function represented, would be sine of x. Boy, that's the messiest one I've written in a while. Sine of x all over x.
I have a question.
Yes, go.
I'm just confused on how you determine the nth term.
Nowhere did it say anything about an nth term.
Just like in general.
Oh, you want to?
Do that. Yeah, because I don't know how.
Well, you could do it one of two ways, my friend. You could. I'm just a little bit. I hope you understand. I'm a little leery of doing this because I feel like you might take the ball and run with it way further than you need to. But here we go. I will take that risk. So plus dot dot dot. As you saw up here, I guess it's not up there anymore. The nth term for sine is this: x. Oops. Negative 1 to the n. X to the 2n plus 1 over 2n plus 1 factorial. So Hayden, here's one way you could do this. If you divided everything through by x, like we did, you could also then divide the nth term by x.
So you just split over x?
So you could go plus, this would be a really raw form, but you could say negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial, and then times x in the denominator.
Okay.
You could then from there simplify it.
I like that.
All it would do is cancel out with the plus 1 in the top exponent. You could do it that way, or really honestly what you could do is you could do it by thinking about a pattern. Here'd be the pattern. You could look at that and say, well, hey, it's alternating, so negative 1 to the n. Check this out, Hayden. I'll try to give you the full explanation here. And then if you look, the numerator is always going to be x to some positive exponent, like 0, 2, 4, 6, 8, 10. And so that would be x to the 2n. But then at the same time, you look at the denominator and say, well, those are all odds, like odd factorials. And so you'd say, well, that's going to be 2n plus 1 factorial. And then I always do a mental check to make sure that I'm not off, like out of sync a little bit. So if I say, all right, well, if n is 0, how does this work out? It works out to be 1. If n is 1, does it work out? Yep. If n is 2, does it work out? Once I get up to like 1, 2, or 3 on my n value, then I'd say, okay, I think we're good. So you could do it one of two ways, either one of those being acceptable. Just know that if you did it the first way, Hayden, you might have to simplify a little bit to try to match it up to something else. Okay, so let me erase this real quick, and let's see here. That will, I think, will be okay. Let's try a few more of these. What if I had the exact same instructions, use a known series to find what this is, to determine what function this is. And let's say I gave you this. Gave you that series right there. Use a known series to determine the function that would go with that series. Bless you. First thing you want to do is look at the denominators and match up those, and then try to take it from there. So did anybody decide what kind of your base is going to be?
1 over 1 minus.
It's the geometric, right? Okay. So if it really is 1 over 1 minus x as far as a base function, 1 over 1 minus x is 1 plus x squared plus x cubed plus ... How has this been changed? Hello? How has this been changed? It's been multiplied by x squared, right? Because all the degrees are 2 higher than they used to be. And so I think we could say then that this equals x squared over 1 minus x. Make sense? Let's do one more. This would be a little more challenging, perhaps. Okay, so here is a series. So once again, please look at this, determine the function that could or that does generate this particular series. Yeah. Again, use your denominators to give you a hint about what base series this is. And so you can figure out what's happened to it. Because whatever's happened to the series would happen to the function as well.
I know what's happening, I just don't know how to represent it. Which is plus
Interesting. Yeah, I just made this one up totally on the fly. I'm thinking that yours works. As far as like I was thinking of a slightly different version. But I think you definitely want to, you definitely have to do the stuff on the left side. You definitely have to do that. I think there's a slightly less complicated way of doing this, but yeah, you definitely have to do the DDX.
So I know how to make it work with n, but that's not what you want.
There's no n's anywhere.
Well, like I know the nth term.
Okay. Oh, okay. That's cool that you know the nth term. That could be a useful. That is a useful skill, but that's not particularly useful here when we're trying to find the series that made this, or the function that made the series. Okay, so let's establish this. Like, which base series are we talking about? It's got to be geometric, right? So that's what I would start off with first and say, all right, geometric is 1 over 1 minus x equals 1 plus x squared plus x cubed plus ... whatever. And now what you've got to see, and this is part of math, this is part of your skill we want to try to work on and develop. We want to see a pattern. So when I compare my first term with my first term, you might look at this and be like, hey, they're the same. Yeah. I suppose I can see, Jasper, why that would lead you to say what you said. I see something else going on, and please forgive me if this is less than perfect, because I did make it up in like 12 seconds. So if it's less than ideal, that's okay. I can accept that. Sydney, you had your hand up. What were you seeing? It's simply the derivative. You notice how x, like there's an x squared and then there's a 2x. There's an x cubed and a 3x squared. All of those are like derivatives of each other, right? So what I was thinking, here's what I was going with here. I was thinking if we did ddx of both sides, we would get ddx of this equals, well, the derivative of 1 is 0. Derivative of x is 1. The derivative of x squared is 2x. The derivative of x cubed is 3x squared. We can think one step ahead. It would be x to the 4th. The derivative of that is 4x cubed. And then we would have a perfect match. So I would say it's the derivative of 1 over 1 minus x squared, or 1 over 1 minus x. There we go. And so Jasper came upon something like this. His question was, okay, I think I've got the pattern figured out. Do I need to express this as like a completed derivative, or can I just leave it like that? You definitely would want to complete the derivative. This is a calculus class, and so you're always okay to leave some arithmetic undone. You know, if it's just like 5 plus 7, it's okay. But if it's calculus you're leaving undone, that's not such a good thing. So I would, if I was going to flip this up, if I was going to do this, I'd flip it up. So it'd be d dx of 1 minus x to the negative 1. And so that would give us the negative of 1 minus x to the negative 2 times negative 1. So I think we would get 1 minus x to the negative 2 for our final answer, if you multiplied the negatives times each other. So again, just another example there of what you could do. You can mess around with these. You could do, I mean, if you wanted to, you could do derivatives of sine or cosine. That would get sort of confusing because the derivative of sine is cosine, right? So there'd be two different answers that could be that would be totally valid. So I don't know if that would be a great question. It could be, hey, here would be a question that would be good for you to think about. You know, you could prove this to yourself. Prove using series that the derivative of sine really is cosine. Or prove using series the derivative of cosine is really negative sine. That would be something you could do pretty easily. Maybe it would complete some good stuff for you. We don't have time this morning, though. So I hope that was good. You got 2 bonus examples there. Bottom line is we have 2 more that I want to cover with you guys. And if we leave a couple of them undone, I'm not too worried about it. There's like a handful, I think like 3 of them that I look at as like over and above and beyond what we need to do. So I want to make sure that we cover the ones we need to cover. So the ones that we definitely need to cover are these 2 right here, numbers 13 and 14. Numbers 13 and 14. So take a look here. I'd like to do this kind of in a similar fashion to what we did earlier. I'd like to do number 13 with you and have a lot of back and forth. I'd like for you guys to try number 14 on your own. Number 14 is somewhat similar to 13. So here we go. To me, the first 2 words are the most important words. It says using integration. So that tells me that I want to set something up that I then integrate. In other words, if I don't ever integrate in here, I'm going to have a little problem. It's specifically saying use integration to do this. So we want to set that up. Using integration, write the first 4 terms in the general term of the power series for ln of 1 plus x. And so I want to think here about how I could set this up, because I'm going to be using integration. And so I'm going to start off by this. I'm going to say, I got to integrate. I was told specifically I must integrate. So I'm going to write integral of, I have no idea, is equal to ln of 1 plus x. So if it's okay with you, could we start off there? What kind of an integrand would generate ln of 1 plus x? 1 over 1 plus x, a fraction, yeah. So if I say, okay, knowing what I know from old stuff here, I know for sure that if my integrand here was 1 over 1 plus x, then I would have exactly what I want. So then the next question becomes, okay, how on earth am I supposed to figure out the series for 1 over 1 plus x? Right? Well, let's think this through. What does that look an awful lot like? There you go. So this will be a little bit of work in between. So I'll just put a little squiggly line here. I'm going to say 1 over 1 minus x. That's equal to 1 plus x squared plus x cubed. And I'm going to go ahead and include that nth term in there, because it did ask for an nth term. So that does not exactly match what I want. How could I turn this into what I actually want to integrate? Substitute negative x. Good. So it'd be 1 over 1 minus negative x is equal to, it's just going to create an alternating pattern, 1 minus x plus x squared minus x cubed plus plus negative 1 to the n, x to the n. Sure, but I like to kind of isolate the alternating element. So we all know, of course, that minus minus is really plus. So I have the series now for the thing that I want to integrate. So now I'm going to return to my original intent, and that was to integrate. So I'm going to integrate left side and integrate right side. That'll make my left side exactly what I wanted. So that would be ln of 1 plus x equals, and thankfully it's really quite easy to integrate a polynomial. That's one of the reasons why we do this. So it would be x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus dot dot dot. Showed you this earlier, I'll show it to you again. To get an nth term, you can actually just integrate the nth term. Who knew? So it would just be negative 1 to the n, x to the n plus 1 over n plus 1. That would be starting with n being 0. You could adjust your nth term to have n start at some other value. That would just be with n starting at 0 like we originally had it. So big concept-wise, you understand the strategy. Using integration, you want to create a series that goes with your integrand, and then once you've done that, just integrate it, and you'll be there. See how good you're going to do with number 14. Give it a shot. It says using integration, write the first 4 terms and the general term of power series for arctangent of x. It does say include the interval of convergence. I think we've done that enough. I think we'll leave that alone for the moment. I think we've done that about 10 or 11 times already. So, Jasper, your question. Oh, you got an answer?
No, like,
No.
oh, no. So this one, why can't I use this?
You can. All I said was that I kind of like this
Oh, okay.
because I like that from the sense of, in this case, it makes no difference whatsoever. But when you're doing like an alternating series test or an absolute convergence, conditional convergence thing, I personally think having that negative 1 to the n separated out is helpful.
Okay.
But if you wrote it like that, I got no issues at all. That's really good. Yep. Nice job. At the end. Here's where I'd start. It says using integration. And so I know that if I don't use integration somewhere in here, that I have not even followed the instructions. So I'd start off by thinking about what I need to integrate. So I'm going to write integral of question mark is equal to arctangent of x. And as I walked around, I felt like some folks just like knew it instantly. Others really had to stop and think. This goes back to chapter 5, I guess, 5.7. So the idea here would be that the integrand needs to be something very specific, not with a's and u's, but with x's and numbers. Do you guys come up with it? What was your integrand? 1 over 1 plus x squared, I agree. So I'm definitely relying on your memory when it comes to chapter 5, and maybe we've used it several times since, but definitely that's where we want to go. So then we stop for a minute and we think, all right, what kind of series would we get for this 1 over 1 plus x squared? Doesn't that look like a geometric? So I'd start off with 1 over 1 minus x is really 1 plus x squared plus x cubed plus dot 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 plus x to the n. So how do I turn that into 1 over 1 plus x squared, the thing that I want? Is it multiplication, substitution? It's substitution. What do I substitute in there, Chandler?
Negative x squared.
That's right. So it'd be 1 over 1 minus negative x squared is equal to 1 minus x squared plus x to the 4th minus x to the 6th plus dot 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 plus negative 1 to the n x to the 2n. Once I've got that, I would need to remember, of course, that minus minus is really plus a positive. I've got the integrand that I kind of proposed that I wanted, so now I just need to integrate both sides. So I end up with arctangent of x. I forgot my dx. There we go. Arctangent of x is then equal to x minus x cubed over 3 plus x to the 5 over 5 minus x to the 7th over 7 plus dot 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 plus negative 1 to the n x to the 2n plus 1 over 2n plus 1. Little known fact, do you guys know that arctan as a graph is symmetrical with respect to the origin? Therefore, it could be considered to be just like sine. Different graph, of course, way different graph, but same pattern with evens and odds and symmetry as we had with sine. No factorials. In fact, isn't this crazy? Isn't this just like sine, except no factorial?
What's the interval of convergence?
Well, so I don't know if we have time to do that because class ended 5 seconds ago. If you want to stick around for a few minutes, I'd be happy to do that. So anyways, quiz tomorrow, 9-7 and 9-10. Question tests.
How would you do the interval of convergence?
Well, so yeah, Grace just asked about that. Let's look at it.
Either that or
The key for me would be my nth term, right?
mine is either going to be under powerful or I have
So I'm going to try and squeeze this in right here. So I'd go ratio test, limit, as n goes to infinity. And then it's n plus 1's substituted, right? So this would be x to the 2n plus 3 over 2n plus 3 times 2n plus 1 over x to the 2n plus 1 is less than 1. So when you cancel stuff out, you're going to end up with limit, it would be x squared times 2n plus 1 over 2n plus 3. So as you apply the limit, the 2n plus 1 over 2n plus 3 would go to 1, wouldn't it? 2 over 2. So you just end up with absolute value of x squared is less than 1. Right?
Yeah.
After you apply the limit. So then you think, all right, well, isn't this still going to be endpoints of negative 1 to 1?
I got you. Look that way.
Those are all the numbers that work. So you'd get negative 1 to 1, but with, perhaps some question marks on those as to whether they're open or closed. So do you remember how to test your endpoints?
Yeah, don't you plug them into the,
Plug them back into the nth term.
yeah.
So I'm going to come back up here because I'm out of room. So I'd say for x equals negative 1, my series would be sigma, and it would be negative 1 to the n times negative 1 to the 2n, oh, darn it, 2n plus, doggone it. I keep hitting the erase button. There, did it again. 2n plus 1 over, where did that go? Over 2n plus 1. So then you look at that and you say, all right, what's going on? I'll do a couple of test values. So if n is 0, gosh, it looks like, let's see here, if n is 0, the top would be 1 times negative 1, right?
Yeah.
So that would be a negative. If n is 1, it would be negative 1 times negative 1. So that would be a positive. So based on that, it looks like it's going to go negative, positive, negative, positive, negative, positive. You could do a few more terms. That's alternating, isn't it?
Yeah. But isn't it?
And it goes to 0.
It goes to, the terms go to 0. So you can either say by AST, or it's an alternating harmonic.
Right.
It converges.
Okay.
So I would just say converges because it's an alternating harmonic. Or you could say I use the AST. So I would say that we close this right there. And then I think when you go for x equals 1, I think you end up with an alternating series again. So you'd say, it converges because of an alternating harmonic. So I think we'd close that one too.
Wait, it's not an alternating harmonic when it equals.
I think so, because wouldn't it be negative 1 to the n
Oh, yeah.
times 1 to the 2n plus 1? So, hey guys, we're trying to finish stuff up. Hold on. So 1 to the 2n plus 1 is going to be positive 1 regardless of n. Negative 1 to the n will alternate.
So, yeah.
And so you'll still get an alternating harmonic. So that would be another convergence on that right end point. So it would be double closed.
Cool.
Be double closed there. So this follows the pattern that we talked about in regard to when you take series and you manipulate them, whether it's a little bit or a lot. unless you move the centering point, the interval of convergence should remain the same with possible changes at the endpoints. Here we saw 2 changes at the endpoints. On a previous one, I think we saw just like 1 change at the endpoint. So I think you can be pretty certain that your interval of convergence, unless shifted, which we didn't, will stay the same. Just test the endpoints to be certain about the convergence on the endpoints.
Thanks.
What was the thing that you did before plugging them in on the bottom?
Say it again? What was it that I did?
I think that's the like,
You're talking about this right here?
Mr. Anderson, will
yeah,
you
all of
be here
that.
after school?
What, say again?
Will you be in this room?
Yeah.
Yeah.
I was doing the ratio test.
Okay. Why?
So the way you always do that for interval of convergence, because the ratio test gives you a very definitive way of determining convergence. Like if you do the ratio test and you get something less than 1,
Yeah.
it converges. So if you think about all the other tests that we've done, like the integral test is kind of a comparison. The 2 comparison tests are comparison tests. The alternating series test only works for alternating series.
Yeah.
The geometric series test only works for geometric series. The ratio test is the one that has the broadest application, and it has a clearly defined mark of this causes the series to converge or diverge. So if you are ever asked for radius of convergence or interval of convergence, always set up a ratio test less than 1, which is right here.
Yeah.
If you set up a ratio test less than 1, what you're saying is I'm looking for convergence. In fact, I'm looking for the x values that allow for convergence. So you
Okay,
always
but
use
you
the ratio
can't-
test.
You can't just go right to the other, or you're just plugging in -1 to the.
Well, so in some cases, maybe you could, right? So the principle is that when you have an alternate, or not an alternating series, when you have a known series, like one of our 4 known series, and you know the interval of convergence, as long as you didn't move the centering point, then the interval of convergence should be the same on your manipulated series.
Right.
Or, well, I take that back. Like if you like substituted x over 2, then your interval of convergence just doubled.
Right.
Right? But my point being that once you've made, we looked at a couple of those. Hey fellas, hey fellas, we're still having class. Sorry, I know. Just please be quiet. So in those cases, yeah, you could jump to endpoints, but you were kind of asking, what in the heck is that all about?
Yeah, like
So that's why I was explaining.
I know what it is, but I just don't understand like why I really had to do that as like a step in between.
Because I felt like it.
Okay.
I
we
suppose I
didn't-
could have started at -1 to 1 and just tested endpoints.
Okay.
I felt
But
like,
like if we don't do that, is that a point off? Do we need to go through that?
well, depends on if you're going from a known series or not. If you're not going from a known series, I don't see how you could start with anything else. But if you're going from a known series,
Uh-huh.
then I think you probably could do that.
Yeah.
You could say, okay, here's my known series. Here's how I changed it. Did that affect the interval? Did it move the centering point? Did it expand or squeeze it down? And then just test your endpoints.
Okay.
So what I'm talking about is like if you had this series and you substituted like x over 2, then in your series, I'll do this in this little box here. So like if you substituted x over 2, like if you know that your original convergence is this, and you substituted x over 2, to find your new interval of convergence, you would substitute x over 2. And then you'd multiply by 2. Now we did 1 or 2 kind of like that. Oops. Like that. But it's been a while. But even then, still, you'd look at that and say, okay, I need to test my endpoints.
Yeah.
So,
Okay. All right, I got that.
okay, cool.
All right. Sweet.
Thanks for your question. Yeah.
Okay, so.
So, sorry.